All right, everybody, hello again. We're going to take a look at the Band of Stability worksheet now, work through some stuff, talk about it a little bit, and hopefully set you up for good success on it. So what we're talking about in this worksheet is whether an atom is stable or unstable, which means radioactive. And so we've talked about stability and instability before when we did the build an atom simulation. You could build the atom and you could click the stable or unstable box, and you saw as you added different amounts of protons and neutrons that the atom would either be stable or unstable. As a quick aside, we have also used the term stability to talk about the electrons. And this is a different form of stability, and this is where it can sometimes be a little confusing. Stability of electrons, getting up to having a full valence electron shell, is different than stability of the nucleus, how many protons and neutrons it has. And that's what we're talking about here, stability of the nucleus. So what I want to take a look at is thinking about this. So remember that the number of protons and neutrons affect the stability of the atom. They affect it because we know that protons won't stay together by themselves. And the reason for that is if I have one proton and another proton, they both have a positive charge. So they're not going to attract to each other, they're going to repel and push away. Positive and positive will push away from each other. And that's what protons want to do. Now, there is also a force called the strong force that will hold them together, and you could maybe get like 2 protons to do this for a little bit. But really what you have to have is you have to have neutrons in there as well. So the neutrons add more strong force to hold these protons and neutrons together, and the protons will try and push away from each other, but they won't push apart from the neutrons because the neutrons have a neutral charge. So we have 2 different forces at work in the nucleus. We've got that electrostatic force, the positive protons pushing away from each other, and we have the strong force, which is a completely different force, and it holds them all together, protons and neutrons. But they have to be really, really close for the strong force to work, which is why you will never, ever feel anything like the strong force, even though you might feel electrostatic force. We've got that going on, and so you have to have enough neutrons in the nucleus in order for the atom to be stable. So thinking about this worksheet, one thing I would recommend, you'll have to use the isotopes of elements graph to complete this assignment. It is at the end of this worksheet, but I've also opened up just another tab so I can flip back and forth to it without having to scroll up and down on my worksheet. Just makes life that much easier for me. All right, so looking at this graph, a few things I want to explain right off the bat. First off, the number on the x-axis down here, this is the number of protons. And the number on the y-axis here, this is the number of neutrons. So it's important that we're not thinking about them as this as the mass. So protons and neutrons are the sides of this graph, the axes of this graph, and we want to focus on that rather than protons and mass number, for example. All right. When you're looking at this graph, you're going to look at all of these little pixels that represent, the little squares that represent an atom of each element. And so things you might look at is you might notice that this element right here has 1, 2, 3, 4, 5, 6, 7 isotopes listed on the graph. And if I want to figure out what element that is, I'm going to scroll back down to the bottom and see that it's 55 is this line. So if I scroll back up this line, then this is probably 56, and then 57, 58, 59, 60. So they all kind of match up, and this is kind of a tough graph to look at. It's not perfect in any way, so I would recommend just being careful as you look through it. It's especially tough, I think, to look at on a computer screen, and I apologize for that. If you're having problems and if you have access to a printer, you can maybe try just printing up this graph just so it looks a little better, and you can make marks on it more easily. So that's one thing I might suggest. other things I might suggest. If you print it up, use a ruler to line things up, just to follow what you're doing. It's helpful. All right, so when we're looking at this, if it is a dark box like this, that means that is the most abundant isotope. It means it's the most common isotope of that element. So you remember when you did your element project, you had to look for the most common isotope. This is the one you were looking for. So it'll tell you the number of protons. So for example, if I look at this one, it's 30 protons, and right about here, so it looks like about 34 neutrons. So zinc, most commonly, element number 30, has 30 protons and 34 neutrons. There are other isotopes of zinc, for example. So it might have 36, it might have 37, 38, or even 40 neutrons. Now, you see, those are other isotopes. They're all found in nature. They're all okay. They are none of them radioactive. They are none of them unstable and are going to decay. You will notice that there are some gaps. So there isn't a zinc with 35 neutrons. There is not a zinc with 39 neutrons. So if something's not on there, it means it just doesn't really exist in nature. And if it has a white box, kind of like this one right here, and this one right here, those are radioactive isotopes. That means they might form in nature, but they're unstable, so they fall back apart. So we've got kind of three levels we're thinking about. Ones that form in nature and are super, super common. Ones that form in nature and are less common. Ones that form in nature and eventually fall back apart. And ones that just don't form. So I guess that's kind of four levels to think about. So anything that's not one of these boxes is one that just doesn't really form. So in order to think about this a little bit, let's start. I'm going to just go through and do a couple of these really quickly with you and help you get going. So iridium 95, or iridium 195. So if I look at this, I'm looking at my element symbol again. Remember, the number on the bottom left is the atomic number, so that is the number of protons. There's no charge number up here, so it has the same number of protons and electrons. And then for my mass number, I'm going to use a calculator to figure this out so I don't have to think about it too much. I know my mass number is 195. I'm trying to find my number of neutrons. I know out of that 195, 77 of them are protons. So that means 118 of them would be neutrons. I'm also going to look at this iridium. Well, no, I take it back. I'm going to look at magnesium here. So magnesium has 12 protons. Again, it is neutral. I see no charge right here, so it's got 12 electrons. And then my number of neutrons is up here, how I figure it out. There's 24 protons and neutrons together in the mass, so I'm going to do 24 minus 12, and that also gets me 12. Now, here's what I want to do. I want to go look at that graph now to figure out if something is common, radioactive, or non-existent. So let's go look at magnesium 24 real quick. So I'm going to come down here. I'm going to look. Here's element 10, 11, 12, right here, 12. And so that's 12 protons. That's also 10, 11, 12 neutrons. So I'm 12 protons, 12 neutrons. I have a black box, so that means it is the most abundant isotope. That means if I flip back here, I'm going to say, yeah, this is super common. You might even delete those, right? Now we're going to come and take a look at iridium 195. So that one's going to be a little bit harder to find on the periodic table, or not on the periodic table, on this graph. So I'm going to follow this line for 75 up, 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 up. And then I'm going to find 76, 77. So 77 is up in here. So here's 77 at 114. 115 doesn't exist. 116. Right here is the most common isotope. 117, 118 would be right here. And there's nothing there. There's no box. There's no white box. There's no gray box. There's no black box. So what that means is this is an isotope that is non-existent. So I'm going to highlight that. I'm going to erase common and radioactive, so I know that. And that's what I want you to do for each of these in here. So I've got 2 of them finished for you. So I want you to think about that. So you should be able to answer question number 2 right now after what we just talked about. Think about number 3. If you're thinking about number 3, maybe go back and look at the last worksheet we did, the isotopes worksheet. For number 4, I want you to look at the graph to kind of think about this answer. Could something with less than 40 protons have the same number of protons and neutrons? And same thing for the large atom. There's also a video at the end of this that you can watch that's super helpful in thinking about why are atoms stable. All right. And then for 6 and 7, you're looking at it and thinking about it again. So here's the one thing I will ask you to remember is think about the difference between mass number and neutrons. So if you have 60 protons and a mass number of 155, think about how many neutrons it would have, and then try and plot it on the graph and see what would happen. And if an element has 90 protons, I want you to look and see how many neutrons it would probably have to have and kind of show where that would go on the graph. If you're doing this, reminder, you can go up to the design here and hit, or up to the menu bar up at the top and hit the draw button. You should have that, and you can draw in stuff on the graph. I think that's about all I've got to say. I will put this video here after this Fuse video here, the Fuse School video. I will put that after this video in the playlist. So yeah, I'll end it right there, and you can get to that video if you want.